let's talk about this worksheet. Now, for a lot of you who are new to second block, usually I record during the second block, and I've got someone assigned to remind me of that, but a lot of times this person doesn't remember. So if any of you think of it, you might just say, hey, it's recording. All right. I didn't say your name. All right. So let's take a look. Let's take a look at the worksheet here. A couple things I just really need to emphasize, and I don't know what it is about this stuff. There are certain things that we struggle with that I sometimes wonder why, and I must not be explaining it right or very well. Like equation of a tangent line, right? I mean, we need a point, we need a slope. You just plug it into that thing, and for some reason we sometimes struggle with that, and it seems pretty straightforward to me. And the thing here on these notes, and I know there's a lot of stuff going on, so yes, it's easy to get confused from that standpoint. But the key thing to this is when you have an equation, understand what the input value is, understand what the output value is, or what it represents. And so when you're asked questions about it, you think about what that represents. That's not about memorizing, something. Are you able to log in, by the way? Have you been able to? Yeah. Okay. All right. What does it represent? And that's why I put this on here. So the most important things here, on these parametric equations, those two ideas right there, these two ideas right here, those are probably the most important. Now, the slope and the speed, yes, those are important also. But this idea of what does, having two equations to represent something, I think, for whatever reason, it's a new idea. So maybe from that standpoint, that's kind of confusing. But when we have a particle, adamant or whatever the case may be, moving around on a piece of paper or something like this, just imagine that as a paved path and someone walking around on this idea of two-dimensional motion as opposed to just going east and west kind of a thing, that at any time, a person starts at noon or whatever, and they're walking around on this path or running or whatever the case may be, at any point in time, t, this person has an x and a y position. If we imagine an xy coordinate set somewhere, wherever the origin is, maybe it's down here, maybe this is 0, 0 down here, right? Maybe this is our y-axis, this is our x-axis, whatever. At any point, so there's three variables, right? There's the time that the particle or the person or the object is on the path, and then there's the position of where that thing is on the path. And there's two parts to its position. There's its horizontal component and there's its vertical component, right? Now, so we have two different equations. We have an x equals equation that has t's in it that tells us what its x coordinate is at any time. And we have an equation that tells us what its y coordinate is at any time. And the x and the y go together to tell us the exact position, right, of where this thing is on this graph, right? Now, we don't have to think of it as a particle moving or a person moving on a path. We can just think of the unit circle, right? You can just think of the unit circle. That's also a parametric equation. But the idea is that at any time or for any theta, there is a x, both an x and a y coordinate on that circle. And, of course, that turns out to be the cosine of that angle or the sine of that angle, right? So that's also a parametric equation. But we're using it mostly as a kind of a position kind of a thing. So these words have to really be important. So I've been talking with some of you, and some of you came in and asked questions, and you're throwing at me things when I talk about what's x prime, and you're saying what's the derivative. Well, oh, yes, I know what's the derivative. But when I say x prime, what would I like for you to say? Yeah, right here, right? X prime. Horizontal velocity. That's what I'd like you to say. Not slope, not derivative, not, right? I mean, in what we're doing, x prime is the horizontal velocity of the object, right? And if we had an x double prime, what would that be? That'd be the horizontal acceleration, right? Position, velocity, acceleration. F, F prime, F double prime. Position, velocity, acceleration. So x prime would be the horizontal velocity, x double prime would be the horizontal acceleration. We don't use that very often. That's what it would be. And same thing with y. Y is its vertical position, its y coordinate, but vertical's better because if we just think of a person moving, we wouldn't necessarily think of an x and y axis, right? So we say horizontal, vertical. And y prime would be its vertical velocity. Vertical velocity. Y double prime would be its vertical acceleration. It's got both. So anytime you're moving in a diagonal in two directions, we have these pieces. Okay, so to the worksheet. I mean, that's the fundamentally most important idea of all of this. So when we have these two equations, understand that. This is the horizontal position. This is the vertical position. All right, so going to number 6. And let's find a presenter today. This person, Brianna. All right. You do get picked quite a bit, yeah.
Someone else needs to experience it.
I think it's a new year. We've started from scratch. What's in the past is in the past. Brianna, I've totally forgotten that you have been the presenter at 17. All right. So here we go. So go into your graph. Do you have this up in your graph screen still, maybe? Oh, well, that's good. Actually, we can start from scratch. So go to your, looks like you don't have anything else. Go to menu and graph entry and parametric. And let's put them in. So what was the first one? It was 0.4t times, help me out, help us out, somebody. Cosine t. And then the y was 0.3t plus 2 sine 2t. Okay? Nope, you're good. Numbers, it'll know that's times. Letters, it doesn't. Okay, go down here and change that 6.28 to a 4 pi. And let's change our window. So go to menu, change our window to -5 to 5. And the y's, we go -2 and 5. Okay? All right. And hit enter, and we've got our picture of Adam. And so did any of you take English in yesterday, third block, get to watch that same?
Yeah.
I did not know that. It's so funny because I have no idea she was doing that. But some of you knew already. That's why I didn't understand. How did you know that? You just knew it was one of the vocabulary.
Because we got them the other day.
You got them the other day, but okay. Because at third block I showed that they said, "Oh yeah, no, we did that in English. They saw this video." I said, "Really?" Yeah, some dumb song or whatever. I said, "Oh, was it this one?" And they said, "Oh yeah, that was it." I said, "Oh, that's funny. The other class will be watching that." Okay, so it's almost like we planned it. But so here's Adam Ant moving around on the page, and it just means that Mrs. Honeycutt and I are both veteran. All right, so. So on number 6, we're supposed to, it says reset your range to the time when Adam Ant comes back down to the origin. Was that what it said? Or comes back down to the x-axis. Right? So, okay, so what we want to do is we want to reset our window. Yeah, it comes back to y = 0, which is the x-axis. So let's go into our window. And that was at about, what, 1.8 or so? 1.7? 7 something. Okay, so let's just to make sure, let's go 1.8. So go window settings again, and we've got. I hit escape out of that. Let's hit escape out. So in other words, what he's doing is he's going up and then he comes back down right here. So we only want this little piece of it here, don't we? So I mean, to me, this looks like 0.2 you know, it's about point. So so let's go ahead and hit a tab actually first, and let's do an arrow up, and let's do our T, instead of 12.57, let's make that 1.8, let's say. Okay, hit enter. So now we only get that little piece of it. And actually, let me show you the zoom. So go to menu, and you can zoom in, but let's go to window and number 2, zoom box. And let me show you how this works. Sorry, Brian, now you gotta use a trackpad. So kind of get the thing up in here somewhere with the trackpad. Okay, up a little higher, up a little higher. What we're going to do is drag a box, go left a little bit, and up just a little higher. Okay, and right there, now click. Okay, and now go down over to here a little bit, just kind of with your trackpad. There you go. And see how it's kind of making a box? It's not as easy as a mouse, obviously, but now just keep coming down all the way a little bit. Well, there you go. Good, right there. And then just click again. All right, so there we go. So now we got a little better picture of this. All right. Now it looks like he comes up and then kind of loops and then is coming back down here like so. All right. Now hit escape and then you'll get out of that. All right. So and then you're supposed to sketch that. So here's where the real important questions I want you to get from this. Find precisely the value at which y stops increasing and starts decreasing. So this is where you've got to think. What does it mean for y to stop going up? Y's member is up and down, right? So what has to happen if it goes up and comes back down? I heard all kinds of stuff yesterday that was not bad stuff, but I heard people saying local max. Yes, that's what's going on. What do we do to find a local max? What's our first step if they say find a local max of something? Do the derivative. Set it equal to 0, right? So yeah, if you were thinking local max, that would be the right kind of thinking, but I want to use the words that I had up there earlier, right? And what does it mean if it's going up and then comes back down? What does it have to do? But the particle has to stop, right? And what's it mean if it stops? If y stops, what's it mean? The velocity. See, there's the word I want is velocity, right? You're talking about position and velocity. That's what I want you to be thinking. It has to have a velocity of 0. Well, it's vertical, so its vertical velocity has to be 0. So that's what they mean by calculation. So that means y prime of t, whatever that equation is, has to be 0. That'd be enough to write down right there. You already have y prime on your paper from an earlier problem, right? So that's what they mean by calculation. Solve that. So go to the calculator. So let's do it. So let's go on our calculator. And let's go to the calculator screen. So hit the scratchpad thing. And let's do a solve. And help us out here, Emily. What did you have for y prime? It was what?
Like the equation?
Yeah, right. What's the equation?
Okay. 0.4. No,
that's x, right? Yeah.
0.3.
0.3.
Plus 4 times cosine of 2t.
2t. And we want to set that equal to 0. And then comma t. And we probably don't need to hit control enter because we have a decimal in there, so it's probably going to do that for us. And then we get we got that N1 stuff. Boy, I hate that. So how do we fix that? How did we do that when we did a solve? And we got that. Remember, it's the 2 pi n stuff. Vertical bar, right? So Brianna, go up and arrow up and grab that equation again. And let's do a vertical bar. Remember, at the end of the solve, we got to remember how to do this, right? So this is a good review right now. So at the end of the solve, we come out here because we're going to be doing this on calculator problems all year long. Doing the derivative, setting it equal to 0, and solving it on calculator problems. Here's what we got to do. And if it's got a trig one in it, we usually want the vertical bar. So what do we want t to be in between?
0.
We already set it in the window, 0 and what? 1.8, right? Remember, we set that in the window. So we want t to be between 0 and 1.8. So 0, and then the less than or equal to, and then the t, and then the 1.8. There we go. All right. At 0.823 is where it stops doing what? No? Yeah, I set you up. I knew somebody'd say that. It's when it stops what? What stops increasing?
Vertical.
Well, okay, now we got to be careful. I said stops increasing, not the velocity stops increasing. The position stops increasing, right? The velocity is actually 0, right? At this point, the velocity is 0. Matter of fact, that's what we just did. We set the velocity equal to 0, right? So at this point, the velocity is 0, but y stops increasing. The vertical. Here's what I really was looking for. The short answer to my question, what happens at this point? It stops going up, right? It stops going up. That's what happens here. The vertical velocity 0 means it stops going up, right? It's not stopped because it might be doing what? It might be going horizontally. It's just stopped going up. So, right? At some point, that stopped going up. But it never stopped. My marker never stopped until I quit drawing, right? The marker never stopped, but at some point it stopped going up. So its vertical velocity was 0, but its horizontal velocity would have never been 0 because it never stopped going horizontal, right? Stopping is a velocity thing, right? That's your speed, right? So, all right, so 0.823, so we get that number. All right, now, okay, well that leads into what I just said. So at that time, 0.8229, whatever, at that time, is he stopped? Now, I just got him saying no, but I don't really know, right? All I really know is what? He stopped going up, right? That's what I know. He stopped going up. So it's not correct to say at that time he stopped moving. We don't have enough information to say that yet. He might have. But all we really know is he stopped going up. So, is he stopped or is he still moving? Justify your answer. So what do we need to do? We need to take this number. Now, I was talking to somebody this morning. Now, that seems like different numbers.
Yeah.
Okay, but this morning we were talking about this, and one way to do it would be, couldn't you repeat what we just did with y prime, with x prime? And what would you be looking for? If you set x prime equal to 0. See if you get that same exact time, right? But, right, I mean, so you could do that, but then is it how many decimal places? And since we got a decimal, I'm not sure that's the best plan. What would be a better plan? I think you guys just said it, but take this number and put it into x prime. And let's see what the velocity is at this time. Let's see what its horizontal velocity is. So let's go back to the calculator. So we're going to go back there and we're going to take, so we've got this works really well. Here's where the vertical bar works wonderfully because we got this. So now we're going to type in, we're not doing a solve though, right? We just want to type in x prime. So what was that? 0.4 cosine t. We'll assume Emily's right. I bet she is. 0.4 cosine t. No, let's actually don't. Just put a t. But we could. Right now you could plug in that 0.822 thing. That'd be fine. But, and then minus 0.4t times sine t. See what I mean? Because I'd have had to plug that 0.8229. I'd probably need about 6 decimal places just to be safe. And then I'd have to plug it like 3 different places. So this is where, now go out to the end. So what I'm going to tell the calculator now is a vertical bar. Because remember, vertical bar means width or such that. So what I want to do is evaluate that expression. Now remember, that's different than solving an equation. This is not a solve. I'm evaluating this. So I'm going to, and I want to put t equals that. But no sense typing it, just arrow up. Just arrow right up and grab it. There it is. So that's going to take all those digits and stick that in there. Now it's really close to 0, right? And As a matter of fact, it's so close you could almost say it's a rounding error, possibly, but since we put in so many digits, I feel pretty good about it. So is it stopped? No, it's moving which way? Well, we know horizontally because this is horizontal velocity, but we know more. Which way? Right, because positive, right? If x prime is positive, x is increasing. Well, x increasing means x going to the right. X prime negative means x is decreasing, which means going to the left, right? So it is moving a little bit to the right. And if we go here and finally, last thing, let's go back to the graph and let's trace. Go to trace in the menu and graph trace, and let's go to 0.8229. Type in 0.8229. Now that's hard to see, so I would like to, we can tell that seems reasonable that that's where it's not going up. Let's do that zoom box again. And let's just do a zoom right around that, where your dot is there. Yeah, right around that top. Yeah, right there. Yeah, right there. Perfect. Okay. And let's do it again. Zoom in again. Oh, yeah, you're still in it. Didn't escape. I think you're still in it. Yeah, you're still in it. Yeah, just let's do a little more. There you go. Okay, now see how it's kind of blocky there? What would we change to make that smoother? T-step. Hit tab. Hit tab. That's what the T-step is. It's how many, it's evaluating it, these little increments. So it's saying it was here, and then at this time it was here, and at this time it was here. And if it's too big of a number. So didn't it, actually they told you to do that, didn't they?
Yeah.
Put 0.01, yeah. So let's go down there and put 0.01. Yeah, that's right. They told you to do it. So go ahead and hit enter. And now it should get smoother and slower. Yeah, a lot smoother. Now let's trace and put in that 0.8229. But now it looks a lot like what I drew up on the board there. It's already there, actually. Good. No, it's still there from before. Good. So they're pretty clear to see. Yep, it looks like it stopped going up, but it's still moving just barely to the right. Right? And it doesn't look like it's going to stop at all. What would the picture look like if it actually stopped? Wouldn't it be a sharp point, probably? Have to be a sharp point, right? Have to be like a sharp point. It actually have to quit going both directions and then go somewhere from there. So it would be, we'd end up with a sharp point, right? Which would mean what? What's the slope at a sharp point? Undefined. Oh, so you're telling me, okay, if it stops, what do we say has to happen if it stops? Sharp point, I know, but I mean with the equation. What's zero? X prime and Y prime would both be zero, right? X prime and Y prime would both be zero. Let's come back to our formulas here. Slope of the path. What happens if X prime and Y prime are both zero? 0 divided by 0. Undefined. Oh, sharp point, so it fits. What if just Y prime is 0? That's what we just got done doing, right? What happens if Y prime is 0 but not X prime? The slope is 0. Oh yeah, right? Stops going up, but it might be going horizontal. That's slope is 0. What happens if it's the other way around? What if X prime is 0 but Y prime's not? What if this was like 3 over 0? That's undefined. What would that look like if Y prime is 3 but X prime is 0? It's going straight up. It's not going horizontal. It's horizontal velocity 0, so it's not going horizontal, it's just going straight up. Oh, what's that slope? What's vertical slope? Undefined, right? It's undefined. Vertical line is undefined slope too, right? Sharp point, slope's undefined. Vertical line, slope's undefined. So this makes sense. That makes sense with what we're talking about, right? Okay, slope of the path is different than these things. Slope of the path, right, is just, here's the path, here's this particle going, that's the slope, but that's different than its rate. And then, of course, the last thing is the speed of the thing on the path. You can have this path right here. It's like the Kearney Trail. I used the example in the other class of Jazzy and me racing on the trail, you know, and we'd start here, and then I'd be way up here, and she'd be way back here, right? same path, but two different objects on that path could have different speeds, right? Have different speeds. Okay, because our positions would be different at different times, right? So it could be the same path, but the speeds would be different. And we're going to talk about what that looks like here in the equation. All right, let's do a problem let's do this problem. Let's just practice using these equations real quick. Okay, so have your calculators out and write down this information. Go ahead and graph it. Go ahead and go into your calculator and graph this. We'll pick a new presenter for this one. Steph, did you get logged in? You don't have your calculator. Casey. Oh, that's not good. I shouldn't do that. I want to do it by random. Okay, go ahead. Don't get this. Oh, I'm sorry. You guys can't see it anymore. Okay, never mind. Here you go. There you go. It's nobody yet. I haven't got anybody. It's going to be a secret.
I would probably cry. That would be so funny.
Now, a question like this would be about as easy as it gets as far as matching the notes, right? I mean, there's no units on this. I haven't talked about Adam Ant and he's moving, or there's no words like, whatever. It just, everything matches the notes perfectly. So this would be the baseline thing I want to make sure you do. And so there'll be some of this on the quiz, right? Just this basic, know the formulas, be able to put them into your calculator, that kind of thing. All right. So you got an X and a Y, which is your horizontal, your vertical position. Even gave you the window, right? What would be a reasonable T-step? I would say leave that 0.1 thing and then just change it, make it smaller if it's if it's not smooth enough, just make that T-step smaller. But I think the 0.1 is usually a pretty good one to go with. Okay? So, and our presenter, drum roll, Caleb. All right. So, everybody getting something that looks like that? Kind of cool, right? You get some kind of interesting. Yeah, you got to get some interesting drawings here. Okay. So now trace on that. I always think this part's interesting too. Caleb, trace on that and start at 0, which would be times 0. So type in a 0. Okay, so that's where it starts. And then just hit your right arrow. It's just kind of interesting to see. Okay, so it's going that way. And then coming back around. And now look what happens there. It looks like it must, what happened out there? That would be an example of stopping, right? That'd be that sharp point. Looks like it goes all the way out and gets to here and then turns around and comes back. So it literally stops in both directions. And then goes back and then is going around and coming back around to that last point, evidently, is about where, what did we go to, 5? So if it gets out there, it looks like it stops and starts. Does it start to come back? Keep going. Yeah, and it actually starts to come back a little bit again until 5. Okay, so that's the scenario we're looking at. All right, now, go ahead and arrow back again. Now, what about the speed? Let's talk about that a little bit. Go back to 0 again, Caleb. let's just talk about the speed of this. Could we get a sense, since we're jumping at 0.1 increments here, is there a way just we could tell something about how fast it's going? Like, is it going at a constant speed or is it changing? Go ahead and hit right arrow. Now everybody watch the dot, okay? And now hit right arrow again, and again, and again, and again, and again. Now, would you say that's going at a constant speed? Is there any information there in what you just watched? Don't you think the gaps, the jumps, how far it travels? Because every time he hits the right arrow, it's a 0.1 time interval. So the bigger jump would be faster, right? It's going faster during that time. And I think at the beginning it didn't move very far at all, did it? The first time he did it. Right now it's jumping bigger. Now go ahead and keep right arrow and let's watch it. So that was a pretty small jump. Right in there as it's turning, it's pretty small, isn't it? Looks like it's slowing down. And in these straight parts, it looks like it's going faster. Now down at the end, it looks like it slows down again. Because right there, that was a pretty small jump. And now it's coming back, right? So that's when we talk about the speed equation. That's what we're talking about there. How fast it's moving along that path. The slope, though, the slope of the path is just this number right here. So the slope is the same here as it was when he was coming this way. Now he's going back this way. The slope's still the same at that place, right? But it's at a different time. And the speeds might be different at those two. Might be. Might not be either. Okay? All right. So, and then what would be the speed? What would be the slope of the path out here on this edge? Wouldn't that be undefined? It looks to me like it'd be a vertical, right? Because that's when it quits going left and starts going back to the right. What would be 0 at that point when it quits going left and comes back to the right? What would be 0 when it quits going horizontal? Which is x prime. So when it goes this way and then comes back the other way horizontally, that's when x prime is 0. When it goes up here and then starts going down, that's when y prime, right? That's when y prime is 0. Okay, so that's what you got to think about with these equations. All right, so now let's just go back and let's do some calculating. So horizontal velocity at t equals 2. What do we need to do? Plug it into x prime. So what would x prime be? Because we're going to kick out a 4, sine 4t. And we plug in 2. So go do that real quick. Do that on your calculator. You have to do x prime, and then you plug in a 2. Right? You would do x prime, and then you would plug in a 2. Oops. What do you get, Caleb? Negative 11.87. $871. 229. So 87. Okay, and vertical velocity be when y prime. So what's y prime here? 3 cosine 3t. Since we're using our calculators, you could actually, let the calculator do it. But they're pretty easy, right? So we're going to do y prime, which would be the derivative of the y equation, and that is how much, Caleb? That'd be. You say it was 3 cosine 3t, so 3 cosine 6. Did I do that right? 2.881. Is that right?
Yeah.
Okay, now, forget the graph for a minute. Pretend we hadn't even graphed it. What did we just learn with those two answers? Don't say it right away, just think about it a minute. What did we just learn with those two answers right there about this situation? This object that is moving on that path that's described by this equation. Okay, go. What do you got?
The velocity, horizontal and vertical at time equals 2 seconds.
Okay. I want more than that. Right, I agree. That's what it is. But what does it tell us about the object? Up and left. You just had, it makes you just had it backwards. Yeah. Up, right? Up and left. That's what I want to say. What does this information tell you about the particle? This particle is going up and left. Why is it going up? Because y prime is positive. Remember the chart. If y prime is positive, y is increasing. Well, what is y? Y is the vertical position. If the vertical position is increasing, it means it's going up. X prime is negative, means x is decreasing. X is the horizontal position. If the horizontal position is decreasing, means it's going left. This particle is going up and left, is what that just told us. Now, let's go back to the calculator, Caleb, and let's trace. At 2, oh, we're already there. Forget it. Hit escape. Just hit your left arrow a couple times. Hit your left arrow a couple times. A couple more times. Left arrow, left arrow, left arrow. Okay, now let's right arrow. So here we come. We're coming in at 2, 1.7, 1.8, 1.9, 2. What's that thing doing? It's going up and left at 2, right? We just found that out. Now, is it going mostly up or mostly left? Mostly left. Is that information in here? Why? A lot bigger number than this number, right? So think of this like a slope. You can think of it like the x slope, but think of the velocity. It's going faster. That's a better way to think of it, not slope, but velocity, horizontal velocity. Horizontal velocity is a lot more than its upward velocity, vertical velocity. So it's going more left than it is up, and surely in the picture it looked like that. See what I mean? See what these things mean? There's a lot of information here. Just got to know what the different things are. All right. Slope of the path. What's the formula for that? Well, heck, we just found y prime and x prime already, didn't we? So isn't it just this number divided by this number? Right? Since it's still at 2, right? It's y prime divided by x prime. Okay, so Caleb, just divide those for us. Good. Go up and grab them so you don't lose decimals. What are you doing? Brianna, are you sure you don't want to be? Go ahead. Delete. What happened, Fred?
Yes.
Did you freeze?
Yes.
I froze. I froze your calculator.
No, you.
Yours is working?
Yeah.
Oh. Boy, some guys will do anything to get out of here. You sabotage this guy. Okay, tell me what you got. 0.0. No, you said 0 point. So pretty flat, but negative slope. Boy, I wish we could look at the graph. But it was up and left, right? It was up and left, right? So is that a negative slope? That's a negative slope, right? Up and left, that would be a negative slope. Slightly negative because it was pretty flat. So that seems reasonable. What about the speed? How do we do the speed? What's the equation? X prime squared plus y prime squared, square root of that. Well, here's x prime, here's y prime. So we just square each of those, add them together, and then do the square root of that. Go back. Are we? Yeah, we're okay. Now, before you hit enter, here you got to fix something. Arrow back to the left. Well, I start over. Because your 2.8 is not under the square root, and this is not going to work because of the negative. Since you're squaring it, do you even need the negative? You know what I mean? But since you didn't put that negative in parentheses, it was going to square it and then stick a negative on. which was going to be bad. So do your square root again. And then do a, now go up and grab that and just take off the negative. Or put parentheses around it could work too. But then, yeah, okay. And then do a plus. Now you got to do a plus right now. So it'll stay inside. There you go. Now arrow up and grab the, we got to square it, but we get that one. Come back. Okay. Now square it. Square that, and then go back and square the other. Now we got it. Okay, perfect. We make a great team, Dave. All right. 12.217. 12.217, and that would be the speed. And again, we always talk about speed's always positive, right? Well, this is going to be positive. Square root, and then squared, that should be positive. So that's the actual speed. Now notice, compare it to this. Does that kind of make sense? It'd be about 12 something? Because the speed, this is the speed going left, is 11 something, and it's also got some speed going up. Does it make sense? So you've got speed going both ways, and of course this is a triangle. That's just Pythagorean theorem, which is basically a triangle. So it's like you've got an 11, you've got 11 this way, 2 this way, and the hypotenuse would be 12 something, right? But most of its speed is from horizontal, little bit of speed from vertical, which makes the total speed that number right there. Okay, we've got to be able to work with those formulas for sure, okay, in a parametric type of graph. That's the basic idea. Now, we'd like to take it into the Adam-Ant situation and know some things going on there. All right, let's move along and let's add just a little to this now. We were talking about same path, different speeds. Let's look at this problem right here now. Let's look at this situation right here. I got two different parametric equations. I got two different ones. Okay? Now, if we graph these, and we'll keep Caleb on the hook here. So let's go into our calculator here. Let's go on our graph screen. Let's tab, hit escape and tab and get into there. And let's delete that. And let's put just a t there. And then let's put t squared in the y. And let's change our, whoops, equals t squared. Let's change our t to negative 5 to 5. Let's change the t from negative 5, whoops, negative 5 to 5. Okay. Oh, do you notice, look at the graph he already has here. Right? It just starts there. Okay, go ahead and now hit enter. See what we get. Oh, interesting. Looks like a parabola. Okay. Now, go into, well, wait, before you do that, let me talk about this. Now, here's something that, another thing we're going to do, and we'll practice this more later. Actually, there'll be a little bit of this on your homework today, so we'll do it a little later today. But there's something called eliminating the parameter. In other words, you notice that when we draw these graphs, they just give us graphs like if we were doing X and Y type graphs, right? But we have this third variable t in here. You can convert most, and some are more complicated than others. We'll stick with pretty simple ones. You can convert a parametric into just its regular function counterpart. In this, and the simplest way is doing it by substitution. In other words, if x is equal to t, and this goes together, doesn't it make sense we can interchange or substitute? Anywhere we see a t, we could put an x and vice versa. So that means if x is equal to t, then right here, the y would actually be equal to x squared. And sure enough, isn't that what that picture just looked like? It looked like y equals x squared. Now the downside of this is that only tells us the path. This doesn't tell us anything about the object on the path. This does. When t is a 1, this particle would be at the x-coordinate 1 and the y-coordinate 1. When t is 2, this particle would be at the x-coordinate 2 and the y-coordinate 4. Does that make sense? So this particle, when t is 1, would be at the point 1, 1. When t is 2, this particle would be at the point 2, 4. Does that make sense? Okay? So parametric equations, we not only know the path, but we know where the particle is on the path. If we have this equation, all we know is the path. Okay? It's kind of like the Lion and the Ranger. When we graphed them, could we tell if they ran into each other? Just by their graphs? all we can tell is what? Their paths cross. But we don't know if they were there at the same time, right? And that's what we tried to find out, right, in those problems. So if all we know is a path, we don't know as much information as we do when we know this. Okay, now, let's look at this one. Okay, so Caleb, let's graph that one in x2 and y2. So let's put t, go down. So in x2, let's put t cubed. And in y2, let's put t to the 6th. And let's do negative 5 to 5 again on there. Okay? All right. Now, what happened? Well, what's the picture look like? They're the same. Oh, but let's talk about substitution here. If x is equal to t cubed, and of course we all know that t to the 6 is just t cubed what? Squared, right? Power to power, you multiply. So isn't t to the 6 just t cubed squared? So couldn't we take our t cubed and substitute an x for it right there, and what do you get? Oh, those are the same thing. But are they the same thing? What about when t is 1? Where is this particle at? What's 1 cubed?
1.
What's 1 to the 6th? 1. What about when t is 2? Oops. What about when t is 2? Where's this particle? 8. What's 2 to the 6th? 64. Oh. So what's that mean? It's kind of like me and Jazzy, right? We were both at 1, 1, and then at t equals 2, she was still back here, and I was way up here, right? Or vice versa. All right, so two different particles. The two different equations represent the particles on the path. Same path, different particles. Okay, so at different times or different places. So speed that would affect the speed, right? The slope at various times because we made different places on the path. All right. So understand this idea on some simple substituting and that kind of thing. It's called eliminating the parameter to get an equation for the path of the object, that kind of thing. Okay, but x primes would be different, right? Your x primes and y primes would be different in these problems, which means your slopes would be different, which would mean your speed would be different, right? It's all based on the x primes, y primes, but they are the same path. They are the same path. Okay, so let's move on. Try that on this one. Eliminate the parameter. Let's try, here's a parametric equation. Here's an x and a y. Let's eliminate the parameter. Well, really, it's two equations, two unknowns is what it is. It's a solve. So what we want to do is we want to take this first one and solve it for t. Okay, so that's what I want you to do here. Take this first one, solve it for t, and then substitute that back into this other one. Take the first one, solve it for t, substitute it back into here, and tell me, and then we'll see what you get. Okay, go. Because when we get to our quiz, which is actually a ways away, it's over a week probably, we got a lot of things to do, so we'll have to spend some time coming back and reviewing this before our next quiz. But this is something I'll want you to do, right? Possibly something you have to do. Okay? And we got something here for me. Y equals what?
4 parentheses, x minus 2 divided by 3 parentheses, negative 3, minus 1.
Okay? Anybody agree with that? I mean, that's not probably, I mean, should we simplify it? Maybe. We've talked about really don't have to. Yeah, you could. I might, if the directions, if I said put it in y equals mx plus b form or something like that, then you would have to, right? I went ahead and did that here, so let's take a look at it. But I think he's right up to a point. Now, yours may look different than that, and it just depends how you simplify. But if you look at mine, whoops. Okay, so we're going to need to solve this one for t, so I subtract 2 from both sides. I get negative 3t there, divide by negative 3, so I get t equals that. And so just like Jane did, he just took that and plugged it back in there for his t. So x minus 2 over negative 3, right there, minus 1, right? That's exactly what he said. So that would be you know, okay. But let's talk about simplifying it. So all I did is I just said, okay, I'll just pull this negative 3 out here, make that negative 4/3 out front, or we could split that apart. A lot of things you could do. Right here, when you divide it by negative 3, to be honest with you, I thought most of you would do this, so that's probably why I did it. But what I would have done here when I divide by negative 3 is I would have written that negative 1/3 x plus 2/3. I would have went like that. T equals, and I would have done that right there. And then when I put that over here, right, in my t, then I could distribute the full. So I probably, when I divided by negative 3, would have done it like that, split it apart. Okay, but anyway, distribute it through there. So that would be in y equals mx plus b form. So we need to be able to do that, right? I mean, that's algebra 1, really, right there. I mean, so we just solve one, plug it into the other, and be able to do that. So what do you got? Well, that's a line. That's a line. Okay, so that what this would be is a line. Okay, when you draw it. Now, what's interesting about it is this is just the path. So the path would be a line. This is actually the particle on the path. So depending on your t step and your t range, you would probably just get a line segment, right? If you graph this, depending on what t's you graph, from what to what, you would just get a piece of a line is all you would really get, right? You get a line segment. And there's going to be a little bit of that in your homework for you to do as well, okay? All right, let's talk about another thing here with parametric equations. The idea of inverse functions. This is another place that parametrics can be kind of helpful. Now, we're on the quiz, probably not going to have you do anything with this, so you don't have to worry about this too much, but I want to show it to you. Okay? So, inverse functions. So, before we get into inverse functions, just look at this. And could you tell me what, if we eliminated the parameter here, if we just wrote its actual yx equation, what would this be? Y equals what? Sine of x, right? Because what does it say right here? X is equal to t. Oh, that's the simplest kind of parametric equation, isn't it? X equals t. Well, then you can just interchange x and t, so I can take t out, put x in, get y equals sine x. So this is just the sine curve. We actually did this one, when we were doing something like this when we were doing the unit circle. But anyway, so maybe after you just saw the parabola we did and you saw this one, you're starting to figure out, oh, if you wanted to do just a normal graph in parametric mode, just let x equal t and then do this, right? I mean, if I wanted to graph e to the x, if I wanted to graph y equals e to the x in parametric mode, I would just do x equals t and y equals what? E to the t, right? If I want to graph some weird parabola, like y equals 3x squared minus 7x, then I would just let x equal t, and I would do y equals 3t squared minus 7t. That would give me that graph, right? I could do that all day long. Any old graphs we wanted, right, we could make them parametric. Now, why would we want to do that? Well, let's pretend I wanted to draw the inverse sine function. I wanted to draw the inverse sine function. Well, what is the number one rule about inverse functions? You do what? If you have an equation, y equals sine x or y equals whatever, and you want to find the inverse, what do? Interchange the x and the y. Oh, in parametrics, we have a separate x and y equation. So to interchange the x and the y would simply mean x would equal what? No. We're going to interchange the x and the y. So x would equal sine t, and y would equal, no, t. We're just interchanging. Interchange the x and the y. So put sine t up here and put t down here. That's interchanging the x and the y, right? Interchanging the x, because remember, if t's a 1, you plug that in, you get an x coordinate, y coordinate. Well, if you just flip those two, you plug in a 1, the x and the y will have flipped. Inverse functions, you interchange the x and the y. Now watch what happens when we graph this. Okay, Caleb, you're up one more time. Okay, so let's go in here and I tell you what, let's just do it with the parabola he's got in here. So go ahead, go up to your x, hit tab and go into your x2, y2, go up into here. Let's delete that one out. And in x1, he's got t and t squared, if you remember. That's what we did. So let's interchange those. So put t squared there. And then put t down here. Okay, now don't hit enter yet. Okay, so we had a parabola like this. And now we just interchange the x and y. So what should the inverse of a parabola look like? What should the inverse function of a parabola look like? Just draw it into here. Maddie, what?
Isn't it on the side?
Remember this? Mirror image in that right there. Wouldn't it be this?
Yeah.
Right? The square root function. The square root function is the inverse of square, right? And this, the top half is the square root function, but this would be your plus or minus, right? I mean, again, think of it. Y equals x squared. You want the inverse. You interchange the x and the y. You get x equals y squared. Solve for y. Y equals plus or minus square root of x, right? That's that right there, right? That's the inverse function. Okay, so go ahead and hit enter. Ah, there it is. And remember, it's not a function, right? In function mode, we can't graph things like this. We'd have had to graph square root of x and then negative square root of x to get both parts of this. But we can graph inverse functions very nicely with parametric equations. All we got to do is interchange them. I mean, right? And we said right here, we could graph any normal graph we want. We can graph any old graph we want by doing this, and now we can do its inverse by just doing that. So, what would be the inverse of this bad boy right here? 3x cubed minus x squared plus 7. Let's go in and do it, Caleb. Go up here. Go up to x1. You got t, go down to y. Okay, leave that t. Okay, we want to do 3x cubed. So what's he got type right here? 3t cubed, right? Because x is t. So 3t cubed, what did I say we wanted? Minus x squared plus 7. So 3t cubed, we want minus x squared, so you're going to put t squared, and it was a plus 7. Oops, or what? Plus 7. Okay, hit enter. Okay. Ooh, can't really see it very well. Let's change our window. Go to your window. Let's go to our Y max. Okay, let's go to our Y max and let's make that about 15 maybe. Okay, now we want the mirror image of that, right? We want the mirror image of that. So let's go tab up there to Y2. How do we do the inverse of that? What are we going to put on this line? No, the top line. Or we're just going to interchange it now, Caleb. So what do we have? 3t cubed minus right, and that was that. Hit enter. Now voila, there's the inverse. Right? Mirror image. Mirror image. Y equals x. Line right here. Mirror image. Inverse function. Okay? So it's a really cool, easy way with parametric. Since you have an x and a y equation, when you interchange the x and y, you can do the inverse. Okay. last problem we're going to do here. Everybody stand up here for about a 1 minute stretch break. Okay, for the home stretch here. Do a few jumping jacks. Maybe a 30-second wall sit if you need to. Reps in wall sits. Yoga, anybody? Shall I see if we can hold the tree pose for 30 seconds? No, maybe not. Isn't that the tree? Isn't that what that is?
Yeah, she has to like go like this.
Oh, you have to do that?
Yeah. Yeah, there you go. I'm gonna have to.
Interrupt my yoga.
It didn't show up when I entered it. So I don't know if I typed it in wrong.
I just don't think you can see it down there. I don't think your windows.
Because it crossed the x-axis, like I should be able to see some of it. But I can try it.
Oh, yeah? 5. Let's change your window here to -10.
Sure. Why not?
And then I think your T needs to go, and your T needs to go -5 to 5. You need to have the same T.
Oh.
Okay, everybody sit down. Here we go. Minutes up.
Did you record it, Steve?
Yeah, it's online. Yeah, it's up there. All right. Okay. Now we want to take, okay, we've talked about velocity and speed equation, all that stuff, and now we want to, kind of like add a map, we want to come in here and we want to talk about a real life situation, see if we can put it all together here. So we've got I spent many minutes drawing this diagram to get it just right. We got the baseball pitcher who seems to be floating in midair, actually, and he's throwing the ball from a height of 7 feet. The pitcher's mound is 60 feet 6 inches from home plate. He's releasing the ball from a height of 7 feet because of the pitcher's mound and so forth. And now I realize the pitcher might actually release it in front of the pitcher's mound a little bit, or in front of the rubber that he stands on. But whatever, we're going to say he releases it from that point, okay, to home plate. And what we know is that information, that this is 7 right here, we know that. And we know that he's going to release it with an initial velocity, horizontal velocity now, of 150 feet per second, right? So when it leaves his hand, it's going perfectly horizontal at 150 feet per second. Now, after it leaves his hand, what's the only thing acting on it? Gravity. Now, in the book, they say we're going to ignore wind resistance, which of course is silly, because then you can never throw a curveball and you can never, whatever. But for this, we're going to ignore wind resistance. Now, later in your homework, they give you a problem where they add in wind resistance. They give you the equation. But we're going to ignore wind resistance. So the only thing acting on it is gravity, which is going to bring it down. And then the question is it a strike? And how fast is it going and all that stuff, which we should be able to get all of that from our equations that we have. Now, the hard part of this one is they didn't give you an X and a Y equation. So what would I label this right here? V sub 0. He throws it. When it leaves his hand, it's got a perfectly horizontal velocity of 150 feet per second. This is X prime. Okay, so what we know is that the horizontal velocity is 150. So I would say to you, from that, we should be able to get an X equation. Because going from X prime to X means to do what? The antiderivative. What's the antiderivative of 150?
Yes.
What? 150 what?
X.
150 T, right? We're already using X for other stuff, right? T is our input variable. 150 T plus some constant, right? Now, how do we find that constant? Well, there is a piece of information we do know, okay? We do know that when T is 0 at the beginning, which is when he throws it, we do know its horizontal position. We're going to call this 0, and we're going to call this 60.5 right here. So what's its horizontal position at time 0? 0. The ball is at 0 at time 0. So what does C have to be? Nothing. 0. So we know our x equation is 150t then. Okay, so we just built that from the information we have. Now what do we know about vertical? When the ball is released, what do we know about y? Do we know its y position? We know at the time it's released, we know its y position is 7. Do we know anything about its y velocity, which would be y prime?
No.
At the instant that it's released, what's its vertical velocity?
No.
We do know. It's 0 because we said the ball's going perfectly horizontal when it leaves his hand. So it is not going vertically at all, so it has no vertical velocity. So at time 0, we know its vertical velocity is 0. And that's still not enough, though, to build ourselves an equation. So I'm going to go to y double prime. Do we know anything about the vertical acceleration?
Yes.
Negative 9.8, but we're going to use feet here, so it's negative 32 feet per second squared. We know y double prime is negative 32 because the vertical acceleration is gravity. So from y double prime, we should be able to build y prime, right? By using the, you're not going to have to do this on the next quiz, by the way. But we should be able to build this with an antiderivative, right? So that'd be negative 32t plus c. Now, how do we find the c? Do we have an initial condition for y prime? We said right there, when we plug in a 0, what's y prime? 0. So what does c got to be? 0. So we can ignore that c. All right, now can we build y from the y prime? We can do the antiderivative again, right? So what would be the antiderivative of negative 32t? Negative 16 t squared plus some c. Now, can we figure out that c? Well, we do have an initial condition up here of y, don't we? When t is 0, y should be 7. That's y is its vertical position. The ball at time 0 is right here. So it's got a y of 7. So we put a 0 in. So what's c got to be? C's got to be 7. So we just built our y equation, negative 16t squared plus 7. Okay, now I would probably give you that in a problem. Okay, but it wasn't that difficult, right? We just hadn't really done one like that before, so you need to see that. But all that information was there. Okay, so there's our x and our y of this ball. So we could graph it and trace and whatever, but I'm not going to worry about it. We kind of know what it's going to do, right? What it should do. All right, so the question is, several questions. When it crosses home plate, is it a strike? And how fast is it going when it crosses home plate? So let's do that one first. How fast is it going when it crosses home plate? Okay, so what do we need here? Probably going to need x prime and y prime, I would agree. So x prime is 150, we already knew that. That's a derivative of that one. And what's y prime? No. Be the derivative of that, negative 32t. Okay. Okay, so got those. How fast is it going when it crosses home plate? Well, don't we have an equation for how fast? What's that equation? The square root one, right? With x prime squared and y prime squared and all that. But what are we missing here? What do we need? T what? T when it... Yeah, we need to know when it crosses home plate, right? We need to know when it crosses home plate before we can do any of this other stuff, right? So when does it cross home plate? Who said that? Macy, say it loud. When x is 60.5. So what would we do then? Right? See what I mean? This is what it's all coming back to what we said at the beginning of the period. You got to know what these things stand for. Horizontal velocity, horizontal position, vertical position. We want to know when it crosses home plate would be when the x is 60.5. So what's 60.5 divided by 150? .403. So in 0.403 seconds, right, I think that's the unit we'd be using here, it's going to cross home plate. Okay? All right. So, what was the question? How fast is it going when it crossed home plate? So what do we do? And into the, oh, there's nothing to plug into X prime, is it? It's always 150 because we're ignoring wind resistance, right? So that ball leaves his hand at 150 feet per second. It's always going to be 150 feet per second. Well, that would be silly, right? Unless we're playing in a vacuum. So we'd have square root. So that'd be 150 squared plus whatever that is when you put that number in there, right? So you're going to take negative 32 times 0.403. You're going to get that value. It'd be negative. You can ignore the negative. You're going to square that, right? And you're going to get a number. Go ahead and get that for me. Anybody?
150.593334.
Anybody else agree?
Yeah.
5, 3, 2, 5,
Yes.
2 3. And that was feet per second, I think. Is anybody surprised by that number? It's going faster than when he released it. Why?
Because it's not down until.
Yeah, because we're ignoring wind resistance. So it's going to maintain its horizontal velocity and gravity's pulling it down, which is speeding it up a little bit, right? So it's actually going faster than we released it, which of course it would not be. But ignoring wind resistance, it would be, okay? So that's our fast. And then is it a strike? We won't finish that part, but what would we do to see if it's a strike? Well, what do you need to know? Well, you're right. See, we have some information we don't know. We don't know how tall the batter is. Where's the strike zone? Okay, but let's ignore that for a second, and then just let's say we did know that. How would we find out if it's a strike? What do we need? No. The height of the ball when it crossed home plate, right? So what equation up here gives us the height of the ball? That equation right there. That's the vertical position of the ball. And so what would we plug into this equation? What is this? What is this right here? The time that crossed the plate, right? This was the time it crossed the plate. So we need to know what its vertical position is when it crossed the plate. So you take the 0.403 and you plug it into that equation because the y equation gives us its vertical position. So you plug that number in, and I don't know, let's say it came out to be 4 feet. That might be a strike, right? Strike zone here to here. I don't know, this would be about 3 feet maybe to 4 feet on someone, 4.5 feet, somewhere in there. So it came out somewhere. So you'd have to have that information. I have to tell you where the strike zone is. Okay? But more importantly is how would you get that? Is it a strike? You need to know its y position. Okay? So that's, if you just understand, again, go back to what we said at the very beginning, what those different equations represent. And you can answer all these different questions. Of course, the only one we didn't do was slope of the path, right? And you don't really care about that probably in this problem, but there'd be a slope at any point along there. There'd be a slope kind of thing. The other thing that could be asked, I think, in your homework, I think it says something like, when does a ball hit the ground? So what would you do? What equation would you care about there? You'd want to know when y is 0. It's on the ground when its vertical position is 0. So you'd set this equal to 0. That'd give you the time it's on the ground, right? And then I think it might ask, how far did it travel until it hit the ground? Well, then that'd be the x equation, right? How far did it travel? That'd be the x position, that kind of stuff. So just all these questions that relate to these, what's going on here. Okay, on your assignment sheet, if you grab your assignment sheet here, we're going to finish up here by getting you started on the homework. So turn to page 249.
I didn't know that.
Two,
249. Okay, so if you look at your assignment sheet, we're jumping around here a little bit. So I've kind of changed the order here of things. So what we're in is 4.4. 4.4. So the homework today is 4.4. So find that. Then we're going to go back to 4.3 and 4.5, and we're going to do a quiz over all three of those sections. And then we're going to do 4.6, but it's not going to be on the quiz. I'll ask about it in the take-home quiz that you see there down the road, and then and at the end on that chapter 4 quiz, a little bit. But, okay, so 4.4, and I want you to skip 11 and 12. You just cross them out. Just skip 11 and 12. And let me see, there might be one other. No, the other ones we can do. Okay, now it starts out, guys, the only thing we haven't done together as a class is what 1, 3, and 5 are about, which I want you to be able to do it, and they just want you to graph it. So I want to make sure everybody can graph these. So the first three, you just graph them on your calculator, and they want you to sketch that on your paper, and it says mark the direction of travel. So if you've got a page, or if you've got a graph that goes like this, and you would copy that, and then you're supposed to mark like at t equals 0. So maybe here was t equals 0, and maybe here was t equals 1, maybe here was t equals 2, and then put the direction of travel. So put arrows just kind of like that. That's what it's talking about. So on the quiz, that'll be something that'll probably happen. I'll give you a parametric equation, probably ask you a lot of questions about it, but one of them might be sketch it, label some points, and mark the direction of travel. And that's what we're talking about there, okay? Just to make sure everybody can get those entered into their calculator properly. Okay?